Hello everyone. Am I audible? Can you hear me? All of you?
Yes, sir.
Okay, great. I will be doing something here. Let me activate the video. Okay, yeah. Okay, so those of you are attending this for the first time, maybe you are seeing this for the first time. This is the INMO 2021 Geometry Session 2. And in the session 1, whose recording is available in YouTube as well, we discussed several things. One of the things we talked about in particular involved
recording. So can you start the recording?
Oh yeah, of course. So let me just start the recording as well. Thank you. So we we talked about several things in the first session, but if I go through that briefly, we talked about invisible points, and some people, I think Arjun said, they are called phantom points. So in literature, that's also used. The second thing that we talked about is the geometric transformation. We briefly defined geometric transformation, or rather gave some examples. We talked about isometries. An isometry is a motion which preserves point-to-point distances. So for example, if you have this piece of rock, and if you take any 2 points on this piece of rock, let's say Q, P and Q, and if you apply an isometry G on this piece of rock, then the output of that process, I'll try to draw it as closely as possible, will also have P prime and Q prime, which are images of the point P and Q, and the distance between PQ would remain preserved. So the distance between P and Q and the distance between P prime and Q prime will be the same after the isometry has been performed. Now, we gave examples of some isometries like rotation, translation, reflection, and so on. Glide reflection will be another one. Apart from isometries, there are other types of geometric transformations which are non-isometries. They are sometimes referred to as, well, some of them are referred to as similarity transformation. And there is a reason. The initial figure and what happens after the transformation, the two objects are similar. Now, the word similar, of course, has meaning in the context of Euclidean geometry, but in the context, in a larger context, we may have to define what similar means, what the word similar means. So I'm not going into that detail here. Just imagine it as the normal similarity idea that is in the Euclidean sense. Okay, and one example of non-isometry we talked about is homothety. And we gave an example of how to think about homothety. So you take a point, a triangle, let's say this is the object on which you want to apply homothety. You can think of it as if you think of the point O, let's call it OH, just to make sure that we understand it's the center of homothety. Then you can think of it as a blowing up point. So you are magnifying OA. This is one thing that you can do. There are other things that you could do. You are magnifying each of these points by the same amount, and you are getting this output triangle, A prime, B prime, C prime. Now, as mathematicians, we have to be very precise when we say magnify it by the same amount. What does that even mean? What's the meaning of magnify by same amount? Well, technically it means that center to center of homothety to image point, this length divided by center of homothety to the initial point, this ratio is preserved. This ratio is preserved. And you can essentially say, okay, if I take a point here, let's say P, and if I take its image P prime, then OA prime by OA would be equal to OP prime by OP, would be equal to OB prime by OB, would be equal to OC prime by OC. You notice that when I'm saying stuff this time, I'm saying this a little bit differently than I said it the first time, because I'm trying to incorporate more precision into what I'm saying. Let's see if that even works further. I want to say that the stuff that depends on ratio, will be preserved under this transformation. So what does that even mean? Well, it means that if there is a point, let's call this point D, such that AD by DB is 2 by 1, then this particular property of the image of D will also be preserved. So A prime D prime by D prime B prime will also be 2 by 1. Instead of thinking about in terms of distances, instead of preserving how far D is from A and D is from B, it's preserving the ratio of the distance of A to the ratio of the distance from B. That's the only difference. Okay, so can you tell me which one of these points, and this is a homework problem, but you can guess a little bit. If I ask you which one of these 4 points, orthocenter, in-center, orthocenter is, okay, let's use the regular stuff. Orthocenter, in-center, circumcenter, and okay, let's use only these 3 for the moment. Which one of these 3 things will be mapped to the corresponding point under this transformation? For example, will the circumcenter be mapped to the circumcenter? Will the in-center be mapped to the in-center? Will the orthocenter be mapped to the orthocenter? This is my question. Oh, the 4th point is, I forgot the big one, the centroid. So my question is this: can all of you doing some little calculations tell me that if AB and ABC and A prime, B prime, C prime are points and images under homothety, will all the will H go to H prime, I go to I prime, O go to O prime, and G go to G prime? That's my question. Anyone? Okay, looks like the best bet is the centroid. Centroid is certainly looks like centroid will be preserved.
And even the in center,
Centroid is preserved. Okay, that is almost immediate because the midpoints will go to the midpoints. And if you take any of them, any one of them, G is splitting them into 2:1 ratio. So certainly G will go to G prime because that ratios will be preserved. Do not, I mean, of course, you can prove it using synthetic geometry, non-rigorous. You can make it rigorous in that sense, but try to see this inflation. Okay, that the midpoint will stay in the midpoint, and the centroid will be at 2:1 ratio from the top and the bottom. So it's stretching equivalently. So it will also go to the same point. Okay, that's great. And someone said in center. Looks like in center would also work. Why does in center work? Why would
Sir, because in center, if I directly the in center divides the line at which it is striking in the ratio of the opposite sides, and the ratio is preserved under homothety.
Very nice. Precisely. Very nice, Devansh. This is exactly what we are trying to hear. Okay, so what he means is that if you take the in center I, this is I prime. So this okay, whatever this is T, suppose this is T prime. AB by AC is equals to AB prime by AC prime, right? Because that's how homothety works. And then it sort of divides the base in that same ratio. So T goes to T prime, and AT prime would be an angle bisector of angle A prime. So I would like to this is what I would like you to do very much. Try to rigorously write down the proof of this. It's certainly this is the core idea, but you have to write. When you write it down rigorously, you will see a bunch of things going in some direction. Okay, so this is good. Next, in center, okay, centroid, okay. What about orthocenter and the circumcenter? Any ideas on that?
I don't think so it holds for ortho center, because if you look at the perpendicular bisector, so midpoint goes to midpoint, but if you look at the perpendicular bisectors, I don't think perpendicular bisectors will be mapped to perpendicular bisectors.
Sir, I think perpendicular bisectors will be mapped to perpendicular bisectors, because we know that using some properties of triangles. Firstly, we know that all the sides of the triangle are in corresponding ratios to one another. They're proportional. They're
Yeah, sorry, Okay, can you guys hear me? Hello? Yes, am I audible?
Yes, sir.
Okay, okay. The internet connection is a bit unstable. I guess that's the issue. Okay, so yeah. Okay, and I'm back. All right. Ryan was saying that he has a way to say that the circumcenter maps to the circumcenter because the perpendicular bisector would go to the perpendicular bisector of a side of a triangle.
No,
Maybe.
sir, I was not talking about the circumcenter. I was talking about the orthocenter.
Oh, you're talking about the orthocenter. Okay. So you're saying that the perpendicular would go to the perpendicular.
Not exactly, sir. Maybe. My point is that could you please like if I wanted to draw two triangles,
Uh-huh.
could you draw the height of altitude going from A to BC?
Certainly, I can do that. Let's do that. So if you have A, B, C, and if you have an altitude, let's say a M, and let's say I have a prime, okay, maybe a little bit less of that.
No, we just need
Yes,
to
I also think that all four will go to their respective positions, but I do not have a way to prove for all of them.
Okay, fine. So this
I
is
know the oil is like what are those circumcenter, orthocenter, and centroid. So if I prove for the orthocenter, circumcenter is proved directly. So don't need to worry about that. But there is some left, like what? Yeah.
okay.
So
Okay. So
orthocenter.
I think you guys are extremely close to, all of you are very close to the idea. So I wouldn't take more time of everyone, Ryan. But I
Sir,
see.
I think I have an idea for ortho center.
Okay, so Devansh is an idea for Ortho Center, which is great. Uh, and you know, all know how I like interactions in class, and I would like you to actually say this. But since we are crushed on time, I will not be able to do that today in the training camp. So I just let you think about it, and if you think you have a way, go ahead and write it down in the WhatsApp group because I think all of you are in that. That would be great. So as a homework, you can try to show all four of them rigorously that they map to each other. Okay, now that we understand a little bit of what's going on here, I'll remind you that we talked about homothety and rotation together. And we say that this is the notion of spiral similarity. And we say that if there are two lines, let's say A, B, C, D, then some of the things that could happen, or rather, I shouldn't even draw the lines. I could draw it like this. So there are six line segments involved using these 4 points. Why? Because you can choose out of four, two of them, right? So to create a segment, so 4 times 3 by 2 times 1, so you have 6 line segments. Okay, so what are the 6 line segments? We have AB, AC, AD, BD, BC, and CD, right? So the question is, what kind of spiral similarity are we expected to discover? So let me just make some room here. Here are the segments. Okay, so one thing that could happen, remember the points should be disjoint. So because you're going to move them, so AB could go to one of these three. So AB could go to BD, AB could go to, so AB could go to, oh, AB could not go to BD, I'm sorry. AB could go to DC. So AB could go to DC. Oh, did I write this same thing? Sorry. BC and CD. Right. So AB could go to DC. So this is one possibility. AB could go to DC, and then we could take AD to BC, right? So this crisscross thing could happen. So let me draw it in a different color. AD to BC. So this is one thing that could happen. Okay. AB, with AB we cannot do anything more, because the only thing that can happen to AB is that it goes to DC. Okay. What could happen to AC? Well, AC could go to BD. Remember, they should go disjointly. So this one goes to this one. So this AC goes to BD. That could happen. All right. And what else could happen? Well, these are the only three things that can happen, right? AB to DC, AC to BD, and AD to BC. Right. Okay, so now one spiral similarity can do two of these at a time. So there are choose two things that we can do. We could do AB to DC, AB to DC, and do the crisscross, or you could do AC to BD and do the crisscross. That could happen. Yeah. So these were the two scenarios that we talked about. So the first scenario was that we take this circle, and we look at the other point O, this other point of intersection O, and this point of intersection will take OB to OC, and will take OA to OD, OA to OD. So B goes to C, A goes to D, B goes to C, A goes to D. So AB goes to CD. That's one way of thinking about it. And the way you should, how does the rotation happen? The rotation is happening in this direction. In this direction. So this is sort of rotating like this. Oops, sorry. This is rotating like this to here. This is rotating like this to here. And we have these lines in the middle. Maybe something like this. Okay, so I should probably do this in this way instead of going over it. So this is one thing that happens. The other thing that happens is that you can think of it in the crisscross manner as well, right? So you could think of it as BC turning into AD. Aren't these two also similar? These two are similar as well, right? So if you think of this one is much more easier, you are sort of turning it down, and it's simple as that. Okay, so we did that, and then we talked about the Meikle point configuration. Meikle point configuration, and this one was quite it had several parts of it. One part was this, that if you have a quadrilateral ABCD, and the way you draw it, okay, let's start with a circle. Suppose you have a cyclic quadrilateral, and I'm going to draw it in a suggestive manner so that it's easier to sort of draw the Meikle point. Okay, so you have this A, B, C, D. Now, what the construction that you do is you extend these two lines, and you have these two P and Q, suppose. And it's possible to show that these four circles all pass through the same point. And we did this thing. And this point M is called the Meikle point of this cyclic quadrilateral, this little cyclic quadrilateral right here. Okay, and then we also showed that PMQ are in the same straight line. PMQ are in the same straight line. PMQ. Given that ABCD is cyclic, PMQ is in the same straight line. And we want
all these lemmas about the Meikle point, can they be used directly in INMO?
Yes. Yes, I think you can. And it's a very well-known result. Now, if you want, if you have some time, then you can, as a side note, put some results about Meikle point, which are pretty straightforward to derive from the basics. But I have seen people do direct references to Meikle point. Yes. Suppose O is the circumcenter of, or the center of this circle. We wanted to show that OM is perpendicular to PQ. Okay, so how do you show that? How do you show that OM is perpendicular to PQ? Did anyone try this problem? So we also say that M is the center of spiral similarity. M is the center of, oh, I should do one thing. Yeah. Center of spiral similarity. And we sort of showed that M would take AD, you think of it as BC to AB maybe. So you basically what you do is you look at this particular triangle right here. You look at this triangle right here, and you show that this rotates into this one. Okay, so how do you show using this picture that OM is perpendicular to PQ? Go ahead, everyone. I'll just give you a little time to think. If you have not thought about it, think about it now. And what I will do in the meantime is draw a better picture, because this picture is terrible. So I will take some time to draw a better picture. So you have a circle here.
Sir, are you drawing all this on the Jamboard?
Yeah, can you not see it?
No, can you please share the link of the Jamboard so that we can also write or draw something if we want?
Oh, okay. So sure. Copy the link and paste it here. Okay, I give the link. Okay, all right. So we
Sir, they are saying access denied.
share. Who has access? Okay. How do you do that? Okay, let me try that. Okay. 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 Right. Now can you try?
Yes, sir, I've got the access now.
Okay. Anonymous alligator is joining. Okay, that's good. Anonymous badger is also joining. Camel is joining. Very nice. Okay, this is fun. All right, so we have this A, B, C, D. Okay, so this is okay, maybe a little bit better than that. I'll do one thing. I'll just, instead of doing this, I will rather do that. Okay, so we have that. Okay, so we have A, B, C, D, P, Q, and then we will draw two more circles. The circumcircle of PAD and the circumcircle of QDC. And they should be intersecting at the Meikle point, and the Meikle point is I'll just use this one, is together in the same straight line as M. All right, that's great. So we have a better picture at least. This is the point. Okay, and we were suggesting that something is happening here. So if I take this as the circle, and if I take this as the circle, okay, so now the thing is that this is D. Okay, so let's carefully understand this. This is A. Let's carefully understand this. Assume that you don't know anything. Okay, because it's sometimes useful to reboot in that sense. So M A D, let's draw this in green. MAD, this one, and MBC. So maybe red. MB, okay. MBC. So this one. So MAD and MBC, they will be similar for a variety of for one reason. Let's use this third circle, which will make this picture very complicated, but nevertheless it is necessary for our purpose. This is the third circle, which is sort of going like this. Okay, so angle BAMC, as yesterday some of you said, angle BMC is equal to okay, so for that actually we don't need this one, we need the other one. Okay, I see. So here is the fourth circle, we need the fourth one for that.
So one idea which I have got to prove that OM is perpendicular to PQ would be that if we draw perpendiculars from O to AB and DC,
just
like if we consider the circle with diameter PO, we only need to prove that M lies on that circle. So to do that, we can consider other points on that circle and somewhat like show that M lies on that circle, and since 3 points have a unique circle, so that would imply M lies on that circle also. Like,
okay, I will go to you, Arjun, in a moment. Okay, just 1 second. Let me just go step by step a little bit. So maybe you're right. Maybe you're right. So
but the problem in that is that we have came back to an angle changing instead of spiral similarity.
Oh yeah. So I would say then. So then don't do that for the moment. So MAD, we want to show that it is similar to MBC. Yep, this is the one. Okay. So these two triangles are similar. How do we show that these two triangles are similar? So just to clean it up a little bit. Okay, how do you show that? Okay, so we see that BMC is equals to BPC because of the angle in the same segment thing. BPC. Okay, so this angle is equal to this angle, but that is equal to this green angle right here because of this small circle, because this is also the green angle, right? So the angle is equal as we expected it to be. So the rotation is okay. I mean, we can think of centering at M. MD is getting rotated to MA. MD is rotated to MA, and MC is simultaneously getting rotated to MB. See, you have to be very clear.
I got to prove to show that triangle MAD is similar to triangle MBC.
Sorry?
I got a proof to show that triangle MAD is similar to triangle MBC.
Okay, yeah, go ahead. What do you have in mind? So we showed that the
Like
two angles are
angle,
equal. The other two angles we can easily show, right? Any one?
yeah,
So we proved that last time
We
that
proved that
similarity of
last
two
time,
triangles.
exactly. We proved that last time. So we can easily say that this angle is equal to this angle, which is equal to this angle.
MBC. Yeah.
Yeah. So the triangles are similar. So we can say that MD by MA is equals to MD by MA is equals to MC by MB. And therefore, this gives us the floating of DC to DAD like this, right? So maybe I can make a separate picture for it. Yeah. Okay. So here we go. So we see that this is the float and this is the float, and so DC is going to AB. DC is going to AB. So if we have the center, circumcenter of this triangle O, and then we have this, and if we draw the perpendiculars from O to DC and O to whatever this point is, what point, let's call this R and S, 90 degrees. So these are midpoints. So clearly R goes to S. R goes to S. Okay, so this is the thing that we stopped out. This is the place where we stopped out in the last class, and today we want to do something even more. So how do you go from here? How do you go from here to proving that
Sir, I think if we want to prove OM is perpendicular to PM, it would suffice to show if we can show that quadrilateral PMRS is concyclic.
PMRS is concyclic. Okay.
If we could show that, then we would be done.
Okay. Yes. But that isn't that absolutely clear from the picture? Because if R is sent to S, so you have to look at this diagram like this. If R is sent to S and if D is sent to A, then the diagram also works in this direction, right? Then D is sent to R and A is sent to S by the same spiral similarity. Isn't that true?
Sir, unable to understand this. D sends to R and A goes to S.
Okay. So, sorry.
Sir, it is true.
It is absolutely true, right? Because the spiral similarities come in pairs, right? So if D is sent to A and if R is sent to S, then D is sent to R, and A is sent to S by the same spiral similarity. So basically this segment goes to this one. Okay, why is that? We already proved this before, but you can say this one more time maybe.
Sir,
Yeah, sir, I think.
Yeah, go ahead.
Sir, I think we had proved that like in these 4 points we have shown that a spiral similarity at M sends dr to as. So we have already like discussed this 4 points ka spiral center would be same, and there would be 3 kinds of spiral similarity. So we are done in some sense.
Yes, basically we are using that particular theorem that if D is going to A and if R is going to S, then D is going to R and A is going to S. This is the pair. This is the dual pair. This is the pair.
Sir, I was thinking of it in a different manner.
Yeah, go ahead.
Sir, because if D is sent to A and C is sent to B, then we are already sending R to S, because R and S are like you maintained proportionality. R is the midpoint of CD and S is the midpoint of
Exactly,
AB.
that's the idea. So you can think of it like this as well, that as Ryan says, that okay, if you really want to understand what's going on, focus on MAB and MDC. MAB is similar to MDC. Do all of you see that? This little piece here, we also discussed this the last time. MAB is similar to MDC, this little piece. Why? Because we already showed that the red angle is equal to the blue angle. Throw away the common part. Throw away the common part. So then this one would be equal to this one. And then you can easily show that this little piece right here is equal to this little piece right here because of this big cyclic quadrilateral. If you don't want to go back to the Michael point argument, then you can say this.
Sir, I think that should be obvious because we are they are midpoint.
So clearly, if MA goes to MB and MD goes to MC, it goes to MC, then A goes to D and B goes to C, right? That's what we had. And the midpoint definitely goes to the midpoint. Okay, so we have, or maybe I just said said it the other way around. Okay, I think I said the other way around. The previous argument was fine actually. So the previous argument was MAD is getting said. Okay, yeah, I think the previous argument is fine. So this is going here, this is going here. So actually no, we have
you shaded triangles MAD and
Yeah.
MBC?
Sorry?
Have you shaded triangle MAD and MBC?
MAD and MBC. I earlier shaded it, yes.
Okay, but in the Jamboard they are still shaded, I think. Anyways, it doesn't matter.
I think it's in a different different jam, I guess. I don't know. We'll see. So now the question is, that we now know that A goes to S and D goes to R. So this is, so M is the center of spiral similarity that takes A to S and D to R. How does that help us to conclude that this is a these 4 points are orthogonal? I'm sorry, concyclic.
Sir, which 4 points?
Uh, the 4 points A,
Sir, some things have froze. Are you writing something on the screen?
okay, my connection is back now. Can you see me? Can you hear me? Hello.
Yeah, we can hear you now.
Okay, great. Okay, so now that we know this, can you directly conclude that ADRS is concyclic?
Sir, is there something known as converse of Mickle point theorem?
The converse of Mickle point theorem. Well, it's sort of the thing that we proved the other time, that if you have two intersecting lines like this, so if you have two straight lines like this, you can just take the, maybe you can use this one to show that this indeed happens. Also use the right angles. There are certain 90 degrees right out there.
Sir, are you asking for the proof of ADRS concyclic?
Yes. Can you show that ADRS is indeed concyclic?
Sir, I Sir, I don't think ADRS is necessarily concyclic.
You don't think ADRS is concyclic?
Sir, because if ADRS concyclic means that angle ASR plus angle ADR is equal to 180 degree, right? Angle
Right.
ASR plus angle ADR.
ASR ADR, yes.
And also we already know that angle ABC plus angle ADC is equal to 180 degree.
Yes.
So angle ABC equal to angle ASR.
Yes.
So we are simply saying that ASR is parallel to BC.
SR is parallel to BC.
ASR equal to ABC, sir.
Sorry, did I just say ADSR?
Yes,
Pardon me.
yes, sir. Yes.
No. I want to say AMRS. AMRS. This one.
Sir, I think that can also be not true, because from the figure it is evident that angle SAM is greater than 90 degree and angle SRM is also pretty close to 90 degrees. So opposite angle sum cannot be 180.
Okay. Maybe you're right. Just a second.
I think you mean I think you want to say PMRS.
Let me just revisit the proof in my head. Okay, PMRS is concyclic. Okay, the circle is there. Yeah, yeah, you're right. We want to show that PMRS is concyclic. That's correct.
And actually, if that would be true, then we would be done.
Yes. PMRS needs to be concyclic. Why is that true? Why is that absolutely evident from what we have already here?
Sir, as a loose argument, but I think it can be easily formalized.
Okay.
So PMAD is concyclic, or is cyclic.
Yes.
PMDA.
Yes.
Now we know that M is this center of spiral similarity, which sends A to S and D to R. Now that would mean that we have some similar triangles given by that spiral similarity. I think we can use some angle chasing there and show that PSM is equal to PRM.
PSM
as an outline of
PSM.
an idea of it.
Okay, I see. Yeah, I mean, exactly.
But sir, we have not learned any converse of Mickle-Point theorem or something like that. So how can we conclude that?
Okay, let's see that. Let's use the information that we already know. We know that A is getting sent to S, and we know that D is getting sent to R. So let's focus on these two blue triangles. Okay, so it means that this angle right here is equal to this angle right here, and it also means that, I mean, since the triangles would be similar, it also means that this angle right here would be equal to this angle right here, because the blue triangles would be similar. This blue triangle would be similar to this blue triangle, right? So this angle right here is equal to this angle right here. Okay, so if that happens, can you immediately tell that PMRS is cyclic?
Yes, sir, it is done because this angle PSM is equal to angle PRM.
Exactly.
So we are.
So basically, by using this arc right here, we are done. PM arc. Okay, so how does that complete the proof that OM is perpendicular to PQ?
Sir, the proof is just direct. Let omega denote in diameter PO. Then we know that points P, S, R lie on omega. And since passing through 2 points, there is a unique circle. So this means that M also lies on omega because points P, S, R, M are concyclic. So M lies on a circle with diameter PO, which implies OM is perpendicular to PM, and since points P, and Q were collinear, so we are done.
Okay, that was fast. Can you say that a little bit? Say your argument a little bit more slowly, so that we can all understand.
So, let omega be the circle having diameter PO.
Omega be the circle having diameter PO. Okay. So let's draw PO, and we have a circle with diameter PO. Okay. So it is passing through S and R, surely.
Yeah.
Okay.
Which this means that omega is the circumcircle of triangle PSR.
Yes, so it will also pass through M.
Yeah. So
Because,
we are done.
Okay, yeah, of course. So basically, this is another circle that is there. It's a cyclic pentagon. Okay, what is happening here? Okay. So, okay. Okay. So can you guys see my screen again? Okay, can you guys see my screen again? Okay.
Yes, sir.
Okay. So we have a cyclic pentagon that is PSO R M P. How do I know? Okay, because if you draw the circle through PSR with PO as the diameter, if you draw a circle like this, then this will be this PSO and PRO are 90 degree, telling you that certainly this is a diameter and these are the angle at the circumference. And since PMRS is cyclic, M lies on the same circle, so PMR is also 90 degree. PMR is also 90 degree, and we are done, right? Okay, so sorry.
Sir, I think you meant to say PMO is 90 degree.
PMO is 90 degree. Yes, PMO is 90 degree. Yes, that's what we wanted to show, right? That PM is perpendicular to OM, or PQ is perpendicular to OM, which is exactly what we wanted. Okay, so that's very nice. We are done. Now, unfortunately, we cannot get into many more things today because I have another class just after this. But I will be trying to arrange another session before INMO, and then we are also interested to sort of create some continuous INMO centric geometry and other sessions throughout the year. We have some plans for that, so you will know about it when we announce it. Until then, we'll stop out here today. Thank you for attending the class.
So just one last thing I want to ask you, can we use the fact that OM is perpendicular to PQ directly?
Oh, no, we can. I don't think we can. Maybe that requires a little bit of exposition. You cannot directly say that.
Okay. And